So I would like to discuss this little set of questions here, and what we will do is just go through them. So use the vision data longitudinal data set. Perform a two-way ANOVA with last refractive status and visit. Select data for age year equals 6. Age year 1 is the all children who entered the study at age 6. Use refer 1 as a covariate. This is the spherical equivalent at the first year in the study. Explore additional covariance structures. Consider at least 5. You can use the 2 you've previously done. And then test the covariance structure on spherical equivalents only. And use your choice for the other 2 types of refractive error. List the structure and the Aki-Ike IC and show which one you would use and why it is appropriate. Okay, so let's look at the vision data set. It says to select data based on age year 1. Now, in fact, we're going to focus on emmetropes and myopes, so I've gone ahead and selected those as well. So it's last refractive status is myope, which is 1, or emmetrope, which is number 2, unless, and we have an and sign. Let's do age year 1 equal to 6. All right. Okay, so there we have, we're looking at kids that entered the study at age 6. Now, I'm just going to get rid of all that. And we're asking about covariance structure, so let's just take a quick look at those. Now, let's just, as a reminder, we have scaled identity, which notice there's no subscripts. So this is the same variance that's used for everybody. The zeros are in the covariance slot. This is if we're talking about within subjects, we have 4 levels, 1, 2, 3, 4. It could be time, it could be lens type, it could be anything that you're doing, repeating the, looking at the subject many times, over in this case 4 times. And so this cell right here represents the relationship between time 1 and time 2, or lens type 1 and lens type 2. And here, all the covariances are 0. That's equivalent to saying all the correlations are 0, with 1 overall variance. So that's kind of a real basic starting point. Another kind of basic starting point is unstructured. Now notice here, there's for the diagonal, which is the variance of condition 1, 2, 3, and 4. Notice the subscripts are all different. So there's a separate variance for each one. In addition, all the covariants have unique subscripts, 2, 1, 3, 1, 4, 1, 3, 2, 4, 2. Notice at the other end of the, this top is equal to the bottom. So 2, 1 is 2, 1, 3, 1 is 3, 1, 3, 2 is 3, 2, and so forth. So those are all, so in other words, 1 compared to 2 is the same as 2 compared to 1. So it doesn't matter if you're correlating height with weight or weight with height, it's the same correlation. So we've got the most that's the most unrestrictive. This is the most restrictive. We have another one that's diagonal, which we step up another step, and each variance is 0, or each variance is different, but the correlations are still 0. So scaled identity, everybody's the same. Diagonal, everybody's different within the variance. So the variance that's around visit 1 is different than the variance around visit 2, different from 3, different from 4. And then the next, I would say, level in our search is compound symmetry. And in compound symmetry, notice the variances, we have our general variance and we have this other little additional variance that's added in there. And those are all the same. And notice that 1 is down here as a 1. So here, all the covariances are equal. They're greater than 0, but they're all the same. So 1 and 2 are the same as 1 and 3, as 1 and 4, and so forth. 2 and 3, 2 and 4, 3 and 4. So compound symmetry kicks it up a notch from the identity and the diagonal to saying there is correlation, but they're all equal. We could look at compound symmetry heterogeneous, which says, okay, in fact, visit 1 has its own variance, visit 2 is a different variance, 3 and 4, but within those variances, the correlations are similar, are the same basically, but multiplied by the effect of the difference in variances between the two. Next, we could look at autoregressive 1, which this is usually used when you're talking about time. You wouldn't do this so much with a lens because there's no real reason lens should be systematically correlated as you go away. But time, if you think about it, if you have two things spaced close together, they're probably more correlated than things spaced a little bit apart or even further apart. And in this case, notice all the variances of time 1, 2, 3, and 4, for those individual times, the variances are all equal. But that correlation between is between 1 and 2, 1 and 3, 1 and 4. Those are different, but they're different in a very systematic way. So, for example, let's say this row is equal to 0.9, or let's say 0.6. Well, it doesn't matter. 0.6. Then, so 1 and 2 are correlated at 0.6. Now, and then to get the variance, you multiply that correlation times that common variance. Here you square it, so 0.6 times 0.6 is 0.36, a little bit smaller correlation because it's squared. That single row is squared. So it's 0.36 times that correlation. And then you multiply that times, then for the fourth condition, or for the 1 and 4, you have 0.36. You square it again, and there you have, so it's cubed, and so you have 0.36 times 0.36 times 0.6 times 0.6 times 0.6, and that's 0.36 times 0.6, and that's going to be in the neighborhood of, I don't know, 0.12 or something. So it's 0.12, so you have 6, 36, and 12 times, points in front of all those, times the standard common variance. And so the variances are, the correlations are a little less as you go down here. And then you can have AR1 heterogeneous, where the variances are different for each time point. Here they're the same, here they're different. And that's all we're going to mess with And so let's just, as a reminder, where do we pick this up? Let's come in here. We're going to go to Vision Data. We're going to go Analyze, Mixed, Linear. We are going to look at the ID. That's the subject ID. For repeated, it's going to be visit. And then for our type of covariance, we're going to do AR1, because we're just going to do one, and we're going to look at visits, and that one makes the most sense. Though you can always look at all of them, multiple ones, and see what happens. If you look at identity, where there is no correlation considered in the 0 is in the covariance structure. One is not at all time 1 is not at all correlated to time 2 to time 3. You get an answer that on the surface, when you're looking at Aki-Ike, it's like minus 3,000 compared to plus 3,000. But you always have to check if there are any warnings at the beginning of your output. And we always look for warnings, because that's going to tell you if it fails to converge. And if the program fails to converge, the output is useless. We have to pick a covariance structure that converges. And that means that it is able to come up with an answer, a minimum least likelihood, or a maximum likelihood. Okay, repeated visit. All right, continue. And now we're going to look at, let's look at spherical equivalents. So, spherical equivalents. And we have the factors are last refractive status. Now, I selected emmetrope and myope, but you don't really have to do that. You can put them all in there and then just look at the two that we had selected. So the answer is going to be, in terms of the variance, will be slightly different because it includes those other two. But since we're going to focus on those two, I just selected them out so that it didn't muck up the data by having these more extreme myopes and hyperopes in there. And visits the other main effect, or visit 1 through, I think 5 is probably the best, or 6, I guess it comes up. And then we want our covariate to be refractive error. So we're looking at spherical equivalence. We want to basically make everybody the same, statistically make everybody the same at the beginning, at when they first entered the study, so that we have that equivalence and then go from there. In our fixed model, or fixed factors, what I do is I highlight the non-covariate terms. So and then I send those over. Let's go in and do that again. Let's get rid of all these so you can see how that goes. So I'm going to just pick the two. Now, technically, first I should highlight everybody. If I don't, because the interaction term with refractive error tells us if we've met the assumption of this parallel factor with analysis of covariance. So in analysis of covariance, you want the baseline and the when you separate by groups, visit or refractive error, you want those guys to be separated in a constant way. And if they're not, if it depends on the level of refractive error as to what the status is, or that relationship, if say the relationship of spherical equivalence depends on an interaction between between these, you want to include this term. You just need to. But for this purpose, we're going to just make the assumption that it's true, even if it isn't, and we're going to put this in. Notice when you do that, you get just these two. You don't get a refractive error, but we do want refractive error in the model as a covariance, so we have to put those in separately. So we have last refractive status, we have visit, we have last refractive status by the visit interaction. Remember, we want to see emmetropes and visits. Does the difference between emmetropes and myopes depend on the visit? And remember, in this case, it probably does, because we're going to start everybody in the same place and then see if they diverge over time. Okay, so we also looking at our statistics. It's fun to look at the parameter estimates because it's like a regression equation, and this will give us information on our refractive error at the beginning, the first visit. That tells us what's happening. So then we can test for the covariance parameters. That just basically says if they're different from 0. We can look at the covariance of the residuals. We'd like for those to be accounted for in our, and they should be equal after we've done stuff, the residuals, after we have done our initial selection of the structure. It should be close to equal, similar anyway. Okay, and then our means, of course, and again we select all three of these. These are our main effects, and usually when we're going to do our plots, we're going to look at last refractive status by visit because we want to look at the means for visit at each level of last refractive status. Compare the main effects. Unless we do our little hack with the with this, we're not going to find the differences there. In fact, well, yeah, okay, let that go. Okay, so all right, so there we go. I think that's everything. Okay. Now here is our Aki-Ike 2487. Now really this number by itself doesn't mean all that much, but before we do that, let's look up here and we look in this block and see if it says warnings. If there is a little title here that says warnings, we don't want to proceed. We've selected probably most likely a covariance structure that doesn't work. Another common warning is, say we didn't put in refractive status in our thing, we would have had, 5, or select any, we'd have 5 refractive statuses for each visit, and we would have gotten an error message saying that each repeated measure is listed more than one. We have multiple entries for each visit, and it doesn't like that. So we now have, we don't have that problem. We've got one refractive status and one observation for each visit for each subject. All right, we look at the information criteria. Aki-Ike, as I said, by itself doesn't make a lot of sense. If we looked at compound symmetry, that number is probably going to be bigger because in this one we've said visit 1 is more correlated to visit 2, more than 3, and more than 4. So there's a relationship there that this would likely pick up. Now it's not necessarily true that it's less, but it could be. All right, here then we look at our test of fixed effects. We see everybody's significant, and that is the last referral. There's a difference between emmetropes and myopes. There's a difference between the visits. There's the degrees of freedom are 6, so we have 7 levels. Last refractive status by visit, we see that interaction is different. So the difference between emmetropes and myopes varies based on visit. And then finally there's the covariate refractive error at age 1, which is significant, meaning that people were different at the beginning. There is a relationship, and it's useful to have that in there. This is our regression equation. Look, this is your A, y equals A plus bx. In this case, the B1 and that's myopia. And so if your patient is myopic, or subject, then you multiply and add minus 1.5. If it's not, if it's emmetrope, then you don't add anything off the intercept. So the intercept starts at minus 5, and then you add a minus 1.5, which is minus 2. And these are diopters of spherical equivalent, and that makes sense that a myopic patient has more negative than an emmetropic person, because the emmetrope is just 0.5, the myope is minus 0.5. And then you can see here that as the visits go up, we're adding a little bit less plus to the diopter. So you start at minus 5 and then you're adding a 0.8. That takes it over, puts it into positive dioptic territory and down there. But remember, when we're looking at visit, we're collapsing across both emmetropes and myopes. This is the interaction term. Notice that whenever the last refractive status is 2, which is emmetropic, we don't add anything to the equation. We just go off this minus 5.5. But if you are if you happen to be a myope, then we do. Now again, this is diopters, and you're adding to the myope at visit 1.37. That's because, and that puts them in hyperopic territory, and that's what myopes do. They start out as hyperopes, and then they go down, 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 down. So this 0.08 is added to the 0.5. Actually, it's added to the 0.5 plus the minus 1.5. So you can see that the number is going down. So they all adjust and give you the predicted value, and that's how those are going on. And then the refractive error, you take your baseline and you multiply that times 0.67. So you're multiplying, you're actually reducing that initial baseline, and the bigger the number at baseline, the bigger the number of diopters you get, which makes sense. You start higher in diopes, you end a little bit higher. All right, then here's our covariance estimates, and notice that our estimate, we find this diagonal. Those were those, this is AR1. So that estimate is the estimate of this variance, which is equal across all groups. If we had done heterogeneous instead of one little diagonal, we would get 4 estimates. And so when you, well, in this case 6, but you would have a separate variance for each visit. So when you're calculating your confidence interval, you have to do it separately for each visit when you're calculating that confidence interval. Okay, so there it is, that one estimate, the common variance between visits is 0.19. That's the variance. Square root is the standard deviation. Square root divided by the square root, that standard deviation divided by the square root of n gives you your estimate of the standard error. This is your pooled variance, and it's the same for everybody, but as far as the standard error goes, it depends on the number of subjects that are involved at each visit. So if you don't have the same number of people, and the number is going to go down over time, people drop out in this longitudinal study, you're getting fewer and fewer numbers, so that square root is going to make the variance bigger, so the confidence interval is going to increase over time. All right, and then we come down and we see our visits. This is collapsed across refractive, so these are this is the overall mean for visits when it's both emmetropes and myopes. We don't use that too often. Somehow I missed refractive status. Where's that? Here it is. Refractive status. So the average across, collapsed across visits. So this is the average myope in diopters across all visits minus 0.5. That makes sense. It's a negative. And they're myopic. And it's 0.4. But remember, they started out hyperopic, so they're not real myopic in this overall average. So what you want to really look at is the interaction term, which gives the myopes separate from the emmetropes. Now, we could have done our little hack where we save the syntax and then put in the comparison and do the paired comparisons. We didn't do that. So notice here, the myopes start in positive territory, so those are positive diopters. They're hyperopic, a little less hyper. Now they've moved into myopic territory, but minus 0.154 isn't really myopic yet. It's still considered normal. Minus 0.65, now we're starting to get into an area where you would be considered myopic. Now, unlike when we do a NIT visit, which is or NIT years, which is the number of years before and after the diagnosis of myopia, people are diagnosed at different levels of visits, so this number is a little fuzzy in terms of when people were actually diagnosed. So we get a general impression here, but it's not very precise. Emmetropes, they also start out pretty hyperopic, but they get less hyperopic, but they don't get as far, well, actually they're all positive, so they never get below, in this case, they don't drop below 0. They could drop a little bit, but the average is above 0. Well, some people are in the negative area. They're not to the negative 0.75 in both meridians, which is the criteria. So that was question 1. Question 2, create the following graph. And so I think you may have gotten slightly different answers. So let's do this one. Again, generally speaking, the answers were pretty similar. So I'm going to move this out of the way. And then we're going to copy this. I'm going to go to Excel. We're going to right-click and paste special. The second one, which gives us a non-formatted answer. And we need to do this for spherical equivalence, refractive error, and or peripheral refraction, and relative peripheral refraction. So that's in there. Let's go back here. Let's go to our vision data or even our output screen. Let's shrink that down a little bit. Let's bring Excel up into here. All right, now we're set to go. We have spherical equivalence, mixed model, linear. All this stuff's going to stay the same. We're just going to change that to relative peripheral refraction as 1. Okay. Come down here, find this chart again, copy, and put it down here, right click, graph there, come down, okay, let's go analyze, mixed, linear. Now we have to find peripheral refraction. Peripheral refraction right here. Whoops, we don't yet need it. Let's continue. Now we find it. Peripheral refraction. Everything stays the same. Okay. Come to the bottom. Copy. Paste. All right, let's make our graph. Come up here. Now, because I selected for emmetropes and myopes, those are the only two things I have here, so I made my life a little bit easier. Notice that it says when you're calculating these means and you're plugging the numbers into the regression equation that we just looked at, the covariate appears in the model or evaluated on the following values. Ref error 1 equals 0.8634. So it adds that same constant value, that baseline. That's how it takes away all the variability from all the others. It uses this one mean value, 0.86 diopters, and applies that to everyone. So everybody starts in the same place. Now, in this column, we have all these little B's. We need to get rid of them. Replace B, replace all. And now we have numbers. Numbers are nice. Okay. So we're going to highlight spherical equivalents, the visit, and the mean. We're going to insert chart. We're going to make it a line chart with dots. We're going to put this, I want to format my axis, and let's see, get my picture out of the way here. Down here we have labels. And it says next to the axis, but we want it at the bottom. There we go. And then I also think it's helpful. Well, we'll let that go for now. All right. So let's go and select our data so we can add some more stuff. We want to edit. And we're going to edit the series name by putting in myopia. Okay. And now let's add something. Let's make it emmetropia. The X values are the visits. And the Y values are the means. Okay. Now before we go too much further, let's look at this and let's see, what do I have on my graph? I need a title, add chart element, axis title. The primary is visit year. The add chart, or not chart title, add axis title. The primary vertical is refractive error. And then some of the things that I did was I came in and made that a little bit bigger to match, actually it's 8, match OBS standards. So for the numbers, they use 8. 8. For the titles, they use 10 and bolded. Now, I guess if you didn't do this, it's not the end of the world, but it's good to get into the habit of, if you're thinking about a journal you want to publish in, go ahead and create those graphs. It's now or later. If you wait, you think you're about done, and then all of a sudden you realize you got to do all these editorial things that the journal editor requires. So they also do not like grid lines. So grid line options are none. Now, they particularly don't like vertical ones, but horizontal ones I think tend to be okay. We're going to add a few more in later, but not right now. So let's go back in, select our data. Oh, I know what else we want. We want to go into the chart design, add a chart element, a legend, so we can keep things a little straight and put it on the bottom. It's just easy there. The other thing we can do for this is my, let's do spherical equivalent. This is emmetrope, spherical equivalent. All right, now let's go in and add some stuff. So let's see, select data, add series name myopic, x value this, y value means for the visit. Okay. Let's add emmetropic. Now notice I'm typing, or I'm highlighting the cell here. That's because I can go back and change that cell and it will carry on to the chart. If I type it in, I don't get to easily modify it without going through select data. So let's do the visit. Y. Okay. Now, this is, and this is, let's go, oops, okay. Well, we don't have to do that yet. All right, let's keep going. We'll label them later. Select data. Now we're down to add myopic. X value is 0 through 6, y is 6. Okay. What just happened? Oh, this is scary. What happened to all my other stuff? Where's my graph up here? What have I done? Let's cancel that. I don't know what just happened. Let's come up here. Okay, there's our relative peripheral refraction. Now let's go to select data. Let's add. Go down here. Let's give it a name. Go to X. Go here. Okay. Add. Symmetry. That was not right. Is it? Okay, let's hope that we've got everything now. Oops, okay. Yeah, now we have everybody. Okay, now we need to change our little labeling a little bit. Let's go to this one is relative peripheral refraction. Symmetry, relative peripheral refraction. Myopic is I didn't make this exactly like I had. I didn't look. PR. Legend titles are a little different. But get the idea. Okay. Now we have things set up. Let's make our graph a little bit bigger. So for purposes of seeing it, to go on with the next question, which is question 3. Carefully look at the figure and write a paragraph or two describing the results. Appropriately cite the analysis of variance terms. Well, we can look back at our output, and here, let's see if we can do that here. And let's see if we can get our graph in there. Let's X out of this guy. And so we can look and see what's significant here. We can show that, for example, let's look at spherical equivalents. Type 3 fixed effects. Now, interestingly enough, this gives us an interaction term, even though, oh yeah, yes, spherical equivalents is this blue line going down, and I'm a little surprised that's as separated as it is, but anyway, you can see these lines are clearly diverging. That's what makes the interaction. For peripheral refraction, that's the blue and the green, that's these two lines. They're also diverging, and so that's going to have a significant interaction. And then we have the relative peripheral refraction, and that has a significant. So we're mostly going to be concerned about the interaction terms because they're all significant. And some of the things we would like to do is, in fact, later we come down and talk about effect sizes at different years across here. But so what I wanted you to see is particularly look at this 0. Now, it's helpful if you insert some additional lines here. So let's bring this back to full screen. Insert shapes, and let's do a line. Let's put this line in at 0 because, in fact, we could do it at even, say, minus 0.5, because, or minus 0.75, like there. And that would give us some information, for example, on spherical equivalents when kind of the average time. This is that fuzzy place, so I'm just going to do 0.5 instead of 0.75. It's fuzzy because the myopes become at different years, so it's kind of a little less clear than it could be due to the fuzzy nature of visit being the year of onset of myopia. We'd really like to do onset of, and in a previous paper that I wrote, we used init years and then we modeled the normal data. So we set up regression with emmetropes only and then filled in all the data, all the data that was for emmetropes based on the information that, like, same age, same gender, same ethnicity, various things like that. We just modeled what emmetropes would look like at the same time points that init years was there for the myopes. So format object. Let's give this solid line. It's a solid line. Let's make it black maybe. Let's make it the width a little wider. We do this just so we can kind of give ourselves a reference point. Below here you're myopic, above here you're not. And that should be enough. And then also I'm going to note that from our init years we see that this crosses, and it crosses so that following this people tend to be myopic. So I'm going to add a line there, insert a line, somewhere, say it just before visit 3. So we're going to pretend like our onset of myopia, the average, is kind of at 2.5 visits. Make that line a little wider and make it black. And then because it's tends to be, if we change the shape of that, it's going to change. I'm going to do control, and that, and the overall box, the figure plus the lines. And I'm going to, oh shoot, I lost it. Control. Make sure nothing changed. Okay. There we go. Control. Now let's right click while we're sitting on that line. You get group. I'm going to group all those things together so that our lines, if we change the shape, moves along with the figure. It doesn't exactly work as well as I would have hoped. Anyhow, this lets us talk about things. So this we're calling the average time people go into the onset of myopia. We notice that prior to onset, this dark blue line is myopic spherical equivalence. And if you look at the, wait a minute, what is that? No, that's peripheral refraction. Relative peripheral refraction. Yeah, so it goes down to the green. So this is this, what is this one? The blue line. That's spherical equivalence. This blue line is peripheral refraction for the myopes. These are two myopic. This is myopic spherical equivalence. That's peripheral. And relative, this guy, this little gray line going up here, is the refraction relative to central. So here, when we're looking at spherical equivalence, it's above the peripheral refraction. So so we're myopic. It's a minus. So it's myopic peripheral refraction before you come to be before you're diagnosed myopic. And the idea with Earl Smith was he said, well, you can control myopia by adding plus. Well, there's plus at the beginning. My question is, why does the person become myopic? But down here, then, it's myopic spherical equivalence is less. So after you become myopic, that's when your relative peripheral equivalence is positive. And people talk about relative peripheral refraction rather than peripheral refraction. So it's just kind of interesting, that little difference right there. And we look here on this gray line, which is the myopic relative peripheral refraction. We see that it crosses over this 0 right about here. Maybe that's where we should have put the line. Anyway, that's what I was kind of getting at. I wanted you to see this and think about this crossover. I think that's kind of an interesting point with this data. Okay. Create 84% confidence intervals using the pooled variance at years 1, 2, and 4 for all 6 lines. List the confidence intervals here. Do not add to the chart which pairs are significantly different. And so we can tell if the confidence intervals don't overlap. Now, what is a confidence interval? Some people had trouble with that, a little bit of trouble. You did it like we have always talked about it, but then you were calling a confidence interval, which was basically the bar, the bar from the mean to the end. That's not really a confidence interval. A confidence interval is mean plus or minus that bar. So there's a lower to upper, and when they don't overlap between things, then, so let's say, for example, year 1, and using the pooled variance. So what's the pooled variance? Let's get this down again. And so let's look at, pooled variance using the create for all 6 lines. Okay, so we're just going to do one. We'll just do the spherical equivalence. So let's look at that. The spherical equivalence, that's this line right. It's these guys, spherical equivalents. Here's 1, 2, and 4. Actually, let's do this guy, which is the peripheral refractive error. Compare the well, maybe not. That's the myope, because I'm asking. Well, I don't specifically ask. I'm asking the difference between those two. Let's look at relative peripheral refraction between myopes and emmetropes. Okay, so that's going to be down here. So we're going to look at comparing year 1 with myope, year 1 with emmetrope. And, oops, that's peripheral refraction. Relative, oh wait, yep, that's relative peripheral refraction. Okay, year 1. So what's our pooled variance? Well, we go to the covariance table. We look at our estimate. Our estimate, we can actually copy this guy. And let's put him down here. Right click, paste. All right, now we're going to our standard deviation, which we need for the effect sizes. We're going to say equals that, equals the square root of the variance. Equals SQRT of that. Now we have a standard deviation. Yes, I need the ends. What a pain in the neck. Okay. And that's descriptive. So let's go in and analyze. I mean, I wish we could just use, go ahead, well, we can't here. Just use degrees of freedom, but it doesn't work out that way. Analyze descriptive, descriptives. Oops, before we do that, we have to split the file. Data, split file, compare groups, last refractive status. Okay. Analyze descriptive, descriptives, relative peripheral refraction. Okay. Oh no. It's by visit. Shoot. Split file, analyze, compare means. I can do it this way, I think. This isn't a legit one way to know, but it gives us the end. Dependent, it's relative, what are we doing that one? And the factor is visit. Oops, visit. Okay. That should give us, oh, I didn't ask for, analyze, compare means, and options, bleeding over. Options are descriptives, Continue. Okay. Now, this gives us the ends for each one. So we can copy this guy, copy, and let's give us lots of room here. Insert. This is probably a lot clunkier than it has to be. Shoot. I'm not sure I like what I'm doing here. Here we go. Insert. Shift cells to the right. Okay. Let's, can we paste here? Paste. Here a little. Paste. Okay, we're off one. Let's move up. Let's go here. I better keep that in there for now. Oops. Delete. You know, there would have been an easier way to do this. I'm going to do the easier way because I am showing you very bad lazy habits. Let's get back to where we were. Let's just insert one row or one little space. Insert. Shift cells to the right. Okay, now we've made a space for our n. Now, copy this guy. Come over here. Paste it. Let's copy these. Oops, these. Notice we only have 17 observations in year 6. We probably shouldn't use year 6. Then we want to put something there. Come over here. We have a lot more emmetropes than we do myopes. Paste. All right. So now we have our standard deviation. This is our n. Standard deviation. We want our standard error. And that's going to be, now notice while we have a constant pooled variance, we're going to have a different standard deviation because we take the standard deviation and divide by the square root of n. So our standard error is 0.04. We're going to do our t, and that equals t inverse 0.16 for an 84% confidence interval, and our n is that minus 1. We get 1.41, and then our little, so let's just call this our error. I mean, we do label these usually CI, but that's not the confidence interval itself. It gives us the confidence interval when we put it in our graph. That equals this times of standard error. And then the lower confidence interval, the lower CI, is equal to the mean minus CI, and the upper confidence interval is equal to mean plus CI. And this is the width of the bar that we see when we, oops, what doesn't it like? Oh. So our confidence interval is really from 0.02 to 0.156 diopters around that mean. So this is what we're interested in looking at. And let's come down to our emmetropes. We got to give ourselves some space here. Let's take this. Now, let's look at our standard deviation. We're going to need to make that a constant, so that's F4. That gives us a $sign in front of the row and column. Other than that, I think everybody is just using everybody beside them. So I'm going to copy this. We want years 2, 4, and then down here with, I think this is here too. 1 there, 2, 4. Okay, those all look pretty good. We can see that the confidence intervals, this little guy, and the plus and minus, they're pretty close to each other. That's because the only thing that differs, they're not exactly the same, even though we're using the pooled variance, because we're dividing by the square root of n. So we look and we say 0.02 is bigger, is bigger than 0.08. So this is the smaller number, and we want to know, do these are myopes and these are emmetropes. This is 0.008 to 0.07, and this is 0.02. So those guys enter, the lower confidence is less than the upper confidence interval for emmetropes, so those are not significant. Let's look at the next one. It is oh, maybe not. Okay, those overlap. Let's go to this one, 0.016. Yeah, see this, the lower confidence dips down to 0.016. Oh, rats. Is that not significant? Oh, that, yeah. Okay, so confidence interval. Okay, I see the error of my ways. See how this guy got shifted over? So the mean is above what is actually the standard error. So this is the mean. So over here, let's see where this confidence interval, The lower confidence interval is the mean minus the CI. That mean is really the error term, so I need to put that there. Okay. And the same way here. That needs to be there. And so now we copy this, paste, 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 paste. Okay, so now let's look and see where we are. We got a minus 26 to 13. We got a minus 44 to a minus 37. So notice that 37 actually is under that 13. So that's different. This is a minus to a plus, minus 0.9. That's a minus 36 to a minus 30. That one is also. So they're significant at all pairs, including this 21. Now that's a positive. 21 and 34 compared to minus and minus. So we would take this minus 20 is the upper limit compared to the lower limit, which is plus 20, and those are real different. So in our graph, which is right here, at year 1, 2, and 4, we are showing significant differences. Now, the next question, what is the effect size between myopes at each of the 3 points? So let's add an effect size here. Effect size. And so we have equals, parenthesis. Let's do the emmetrope as, no, the myope as the test minus the emmetrope divided by the pooled standard deviation. It's right there. And we get 0.48. So that kind of confirms our significance, because that's practically a half standard deviation, and the sample size is way above 30 in each group. So that's going to be significant. Oh, I don't want those. Okay, so you can see we've got a half, 0.7 standard deviation, 1.1. I mean, this is really big differences between the relative refraction in those two. And that's it. Long tape.